Good morning, dear students. Today I've started with part 7 complex numbers, and I hope all of you are working on this particular topic with solved examples as well as with the exercise of a particular textbook. Now, moving with more problems of this particular topic, today, I would start with my first problem, which says if alpha be the positive cube root and beta gamma be the complex cube root of m, a real positive number, then for any x, y, z, show that this is equal to this. Omega is the complex cube root of unity. We start with solution as alpha is is cube root of m, that is alpha is equal to m to the power 1 by 3. This is our first concept with respect to this problem. Alpha is m one third, and it is positive, and it is not complex cube root of m, and and beta is equal to m one third omega, and gamma is m one third omega squared. Now what you observe is that alpha is the real root of m, but beta and gamma are complex cube root of m. Therefore, alpha is m one third, the cube root of m, and beta and gamma are complex cube root of m. We have discussed this particular section in our part 3 of complex number. Now, with this values of alpha, beta and gamma, I would substitute in the left hand side. Therefore, left hand side is equal to x beta plus y gamma plus z alpha by x gamma plus y alpha plus z beta. This is my left hand side, and with these values of alpha, beta and gamma, I substitute is equal to x m one third omega. I substitute value of gamma y m one third omega square, and I substitute value of alpha z m one third, and my again the value of gamma x m one third omega square plus y m one third plus z m one third omega. That means your values of alpha, beta, gamma is substituted in the left hand side, if you make, if you substitute a value which is not this nor this, then your problem would be unsolved. So therefore, if you assume the value of beta and gamma correctly, because they are complex cube roots of m and alpha is the real root cube root of m, assumption of alpha, beta, gamma is very important for this particular problem. And now this becomes very simple. I take m one third common. Left over is x omega y omega square plus z. And in my denominator, I have m one third into x omega square y plus z omega. These two get cancelled. I have taken common. Now I would take omega square common. That means omega square. This becomes x omega by omega square plus y plus z by omega square, and in the denominator let it be as it is, x omega square y z omega. Follow each step. After cancelling m one third, it becomes a simple problem. It becomes a problem which carries 2 marks. And I had worked out this particular problem in my part 4 or part 3 of complex number. Now it has reduced to that particular problem. Now, on further simplification, omega square, I am multiplying omega to numerator and denominator, x omega square plus y plus z omega, and I am not writing omega cube. Omega cube is equal to 1. So omega cube is equal to 1, and my denominator is x omega square y plus z omega. I find these two getting cancelled is equal to omega square, which is RHS. That is, LHS is equal to RHS. A very important problem. It looks very difficult, but actually you would find, after assuming values of alpha, beta and gamma, the problem becomes very simple and easy to work out. And I have worked out this, and my left hand side is equal to right hand side, and this is the complete problem. You work step by step. From here, we move on to this particular step. From here, we move on to this particular step, and this, therefore, we move on to this omega square. This is my problem number 1. I now move on to problem number 2. Problem number 2. In the complex plane, the vertices of an equilateral triangle are represented by complex number Z1, Z2 and Z3, prove that 1 by Z1 minus Z2, 1 by Z2 minus Z3, 1 by Z3 minus Z1 now this type of problems are there in different exams. Even in your Indian Statistical Institute, you would find these types of problems. There are many problems related to this geometrical portion, the Argand plane problems, problems similar to as analytical geometry. Now, as far as this problem is concerned, as solution, as Z1, Z2, Z3 are vertices of an equilateral triangle, therefore mod Z1 minus Z2 mod Z2 minus Z3 mod Z3 minus Z1. This is the very basic step. The given vertices Z1, Z2, Z3 are vertices of an equilateral triangle. When the triangle is equilateral, all three sides are same, all the three sides are equal, and if Z1, Z2, Z3 are their vertices, so definitely modulus of this portion is equal to the three portions. This is the very first step, that the three sides are equal. I square them, that is Z1 minus Z2 is equal to Z3 minus Z1 whole square. I am simply squaring them out. The three sides are equal. Triangle is an equilateral triangle. So therefore, if I square them, then also they are equal. And very important submission I am about to make, that this particular square of modulus can be written as Z1 minus Z2 into Z1 bar minus Z2 bar. You need to pay attention to this very important step. It means that Z into Z bar is nothing but modulus square. An important point as far as complex number is concerned. If a complex number and its conjugate are multiplied together, say for example, z is equal to x plus iy. Therefore, z bar is x minus iy. When that is the case, then if I multiply z into z bar, it is simply modulus square. because left hand side is x square plus y square, which is simply square of modulus. And similarly, I may write z2, z3 into z2 bar minus z3 bar is equal to z3 minus z1, z3 bar minus z1 bar. The very basic step in this particular problem, complex number into its conjugate, complex number into its conjugate, and similarly this is equal to modulus of the complex number. This is number 1. Now, I start with left hand side of this. Left hand side, left hand side is equal to 1 by z1 minus z2 plus 1 by z2 minus z3 into plus 1 by z3 minus z2. This is z3 minus z1. This is my left hand side. I now multiply this, all the three, numerator and denominator, by their conjugate, that is z1 bar minus z2 bar divided by z1 minus z2 into z1 bar minus z2 bar, plus I am multiplying denominator by its conjugate, z1 bar minus z2 bar. Similarly, my next step, z2 bar minus z3 bar by z2 minus z3, z2 bar minus z3 bar. And my third step is z3 bar minus z1 bar by z3 minus z1, z3 bar minus z1 bar. Similarly, I am multiplying numerator and denominator. Follow each step. Therefore, what I find is these three quantities are all equal from 1. Therefore, which can be written as z1 bar minus z2 bar plus z2 bar minus z3 bar plus z3 bar minus z1 bar whole sum divided by, say, z1 minus z2, z1 bar minus z2 bar. All the three quantities from 1, they are all equal. So therefore, denominator of all these three quantities are equal. If that be the case, then if this is equal to this is equal to this, denominator remains same, and my numerator is now equal to 0, because these cancels with this cancels with this, and this gets cancelled with this, and my it is equal to 0, which is equal to RHS, that is left hand side is equal to, I repeat once again, Z1, Z2, Z3 are vertices of an equilateral triangle. Problem number 1 and problem number 2, I am working them out. The reason is they look very difficult. But if your logical sense is correct, it becomes very simple. And for your competitive exams, You have to work these types of problems quite regularly. These are problems which require lot of preparation, lot of solved examples you need to see, and you need to work them out. After prolonged practice, then you would attain perfection. So therefore, this is my left hand side. But what is the two conditions I am getting? The two conditions I am getting, they are equilateral triangles. Therefore, their sides are equal. How do I measure their side? Distance concept not there in case of complex number. Modulus is there. Modulus, modulus, modulus. Three sides equal. I square them. After squaring all three, what I find that this particular modulus of a complex number can be modulus square of a complex number can be written as product of the complex number and its conjugate. I have denoted out here. Similarly, this complex number, this modulus square may be expressed in terms of this, and this may be expressed in terms of this. That is, from 1, I find these three are equal. Now, my next step. I start with my left hand side. I start with LHS, which is this given condition. And from LHS, I start multiplying with its conjugate. I multiply by its conjugate, numerator and denominator, numerator and denominator, and similarly this. Therefore, on simplification, as these three are equal from 1, these three quantities are equal. Therefore, I write any of them you can write. My numerator is equal to 0, which is my RHS. I now move on to problem number 3. Prove that A plus B omega C omega square whole cube plus A B omega square plus C omega whole cube is equal to 27 ABC. If A plus B plus C is equal to 0. Very important problem, and this particular problem is there in our examinations quite often. So therefore, this is the given condition. A plus B plus C is equal to 0, and I have to prove that my left hand side is equal to right hand side with the condition that A plus B plus C is equal to 0. Now, if you recall, I did one factorization, that factorize x cube plus y cube, x cube solution, hint, x cube plus y cube is x plus y, x plus y omega, x plus y omega square. I did this particular problem in part 4 of complex number. Now, we know how to factorize this, and if I assume this as x, and I assume that as y, x cube plus y cube. I have to first factorize it. I start with left hand side. A plus b omega c omega square whole cube plus a plus b omega square c omega whole cube is first, if this is x, if this is y, x plus y, that is this plus this, a plus b omega plus c omega square plus a plus b omega square c omega. This is my first part. So therefore, my second factor is x plus y omega, a b omega c omega square x omega, sorry, a omega b omega cube plus c omega square, and my third factor is a b omega c omega square plus a omega square b omega to the power 4 c omega cube, my third bracket. On further simplification, I may write this as 2a plus b omega plus omega square c omega square plus omega. This is the first factor. Second factor, this a 1 plus omega plus b omega plus 1, because omega cube is equal to 1, because this omega cube is 1, plus c omega square, c omega square, that is 2c omega square. Second factor, my third factor is a 1 plus omega square plus b omega plus 1 plus a 1 plus omega square b omega plus 1 omega plus, sorry, omega plus omega, because omega cube is 1, so left over is omega plus c omega square plus 1. Third factor. Now I am a bit fast. Now omega plus omega square minus 1 minus b minus c, this is equal to minus a omega square minus b omega square c 2c omega square. Third factor, I replace this by minus omega, minus a omega, and this is equal to plus 2b omega, and this is equal to minus c omega. Since again 1 plus omega square is equal to 0. Next is 2a minus b minus c. Taking minus omega square, minus omega is omega cube, which is equal to 1, and left over is 2c minus b minus a, 2c 2b minus c minus a. On substituting a plus b plus c is equal to 0 in 3, I would get 27 ABC, which is equal to RHS. Thank you very much for today, boys.